Welcome to the AWS Outpost Networking Foundation session. I'm Matt Lewis, and I'm a principal developer advocate over here at AWS. And today we're actually going to be diving into a whole bunch of detail around how AWS Outpost networking works. So firstly, AWS Outposts is where AWS is bringing the technology that we've built in our regional data centers to you, to your data centers, to your on-premises. So we're using the same AWS designed infrastructure as an AWS data center, but you can now buy that infrastructure in the form of a rack or multiple racks as an AWS Outpost and deploy that on premises. So AWS Outposts is a fully managed, monitored, and operated by AWS just as if it runs within the regions. So we're managing and monitoring the hardware inside the rack that gets deployed on premises, just like we were monitoring hardware inside a region. From a customer's perspective, you get access to the AWS console where you would manage your in-region resources, but you can do the same thing with an AWS Outpost. And in fact, one of the key components as part of this single pane of management is Amazon VPC. So Amazon VPC, which we'll talk more about, is a construct that runs inside the region that we've now extended to AWS Outposts. And I'll talk a little bit about how that works shortly. So first, when I think about AWS Outposts, I think about three main networking components. First is the Amazon VPC networking, which we're about to dive into. Then there's local area network connectivity. So we're actually taking a piece of hardware or a whole rack worth of hardware, or in fact, multiple racks if you wanted to, and we're bringing that on premises and we need to connect into your local area network of the data center or the on-premises site where you're deploying an outpost. Then from your on-premises data center, we need connectivity back to AWS. AWS Outpost is a fully managed service that requires an always-on connection back to the AWS region. So we'll talk about WAN area or wide area networking as well. So let's dive into Amazon VPC networking. And this is before Outposts. We'll just dive into what Amazon VPC looks like and the components that are involved just to set a foundation here. So when I think of Amazon VPC, I also think of Amazon EC2 because Amazon VPC is a means to deploying Amazon EC2. So both really go hand in hand. Now, an Amazon VPC is a regional level construct, which means it operates within the bounds of an AWS region. So here we have a VPC, and whenever you create a VPC, you choose a region to deploy in, and then you'll choose a CIDR address range for that VPC. So this will be the CIDR range that you'll create subnets from, where you'll deploy EC2 instances. Now we have some other features like expanding the CIDR range and IPv6. We won't dive into those in this session though. So when we think of an AWS region, we've actually compartmentalized the AWS region into multiple availability zones. And an availability zone from an AWS perspective can be considered a grouping of fault domains. So what we like to do, and also to adhere to the EC2 SLA, we like to deploy across multiple availability zones within a region. So the way we do that within a VPC is we'll use subnets. Now I like to think of there being two different types of subnets, public subnets and private subnets. And here we've actually deployed or created 4 subnets, 2 in each availability zone. Then once we've got our subnets, we can go ahead and create EC2 instances. And when you create an EC2 instance or spin up an EC2 instance, you'll determine that a particular subnet where you'd like to deploy that instance, that subnet is associated with an availability zone, associated with a VPC, and associated with a region. So there's multiple different layers that go into deploying an EC2 instance here. So in this case, we're actually deploying 4 EC2 instances, and each are addressed, or the elastic network interface of an EC2 instance for each of these instances is addressed in each of these different subnets. So we've got a 10.10.11, a 10.11.11, a 10.12.11, and a 10.13.11. So these instances can talk to each other, but they're all addressed in different subnets in different availability zones. So when we've got a VPC, we might want to connect to something like the public internet, or we also have all of these services that sit outside of the VPC. And so if we take something like Amazon S3 or maybe Amazon DynamoDB, these services are publicly addressed. So the IP addresses for this service that you reach out to are in the public realm of an AWS region. Okay, so when we have a VPC, we've actually addressed the VPC in what we call the RFC 1918 range, which is a private range. And then we need to determine how all of these instances inside the VPC can talk to each other. And the way we do that is via a route table. So when you create a VPC, you start with what's called the main route table, and that's going to determine everything inside the VPC and how everything can talk to each other or communicate with each other. But then you can create a route table per subnet, and that's always a good idea. Now here we've got a route table for our first public subnet here on the left-hand side. And you'll notice we've already got a route in that route table. And this route is actually what we call the local route of a VPC. So in this case, it's a 10.1.0.0/16. The reason why this local route is so important is that it allows every instance inside the VPC to communicate with each other. So when you create different route tables in different subnets, it will always inherit this local route. And in fact, you can't configure a more specific route than the local route because we use that for control inside the VPC such that everything can talk to everything else. So here we create another route table, and it also has that local route again. So instance A can communicate with instance C. Now, to communicate with the rest of the outside world, you'll notice we're using private addresses or RFC 1918 addresses. And to communicate with S3 or maybe even the public internet, we need a public IP address. And we can then use what we call an internet gateway or an IGW. Now, in the public subnet A, we've now configured a default route or a 000/0 via the internet gateway. We then configure what's called an elastic IP, or in this case, it's a 54.23.12.43. And that's actually a public IP that's configured in Amazon's public range advertised out to the public internet. So now what we've basically got is a static one-to-one NAT from a 10.1.0.11, which is instance A, to the 54.23.12.43. What that allows instance A to do is reach out through the IGW and communicate with public services, but then also communicate with the internet and vice versa. Something in the internet could do an inbound connection to the 54 address, and it would get NATed or a network address translated through to the 10.1.0.11 address and exist or transit down through to the instance A. Now with instance B, we probably want some kind of internet communication as well, but we don't want outbound communication to that instance. So we could use what's called a NAT instance. So in this case, we've got another public Amazon IP, a 54.19.12.23. Again, that's out of Amazon's public range of IPs. And we have a route via instance B, which is our NAT instance in our other public subnet. And then we can route through to the internet gateway and then on towards the public internet or public services. Now, we realized some time ago that NAT instances are a little bit cumbersome to deploy. So we built this service called NAT Gateway, and that's just something that we operate within an availability zone, performing the same NAT function as a NAT instance, just in a more scalable way. So you could use a NAT Gateway there. So as we move along here, we're starting to add different components to the VPC and allowing different traffic flows in and out of the VPC. So now we've got a VPC endpoint, and we have what's called a prefix list, or in this case, an S3 prefix list in our first route table here for the public subnet, and again for our private subnet as well. And what the VPC endpoint is going to allow us to do is communicate directly with S3 and DynamoDB without having to have an elastic IP. Then we could have something like a virtual gateway or a VGW or virtual private gateway, sorry. And the virtual private gateway is going to allow you to connect via VPN to your VPC from on-premises, and then also via Direct Connect, via what we call a private virtual interface. You can also use what's called a Direct Connect gateway. And again, we're building out our routes on the left-hand side here. You'll notice we've now got our on-premises routes via the VGW. Then we can use what's called VPC peering. And when we first built VPC, we thought customers would build one VPC and that would be like their virtual data center in AWS. But as it turned out, customers started building 2 or 10 or 50 or 100. And I actually have spoken to some customers that have over 1,000 VPCs in their deployment. Now, when you have 1,000 VPCs, you might want to connect these VPCs together. VPC peering allows you to connect those VPCs, either VPCs in the same region or VPCs maybe in another region. And again, we need to build our routing for each of the route tables that has communications over the VPC peering connection. Now, about 2 years ago, I think it was reInvent 2018, we deployed a service called Transit Gateway. And Transit Gateway was really to help large scale VPC deployments. So what we can do here is attach a Transit Gateway to our VPC and then connect the Transit Gateway to up to 5,000 VPCs, and also via what we call a transit BIF, connect through to an on-premises, or maybe even via a VPN. And again, we build out our routes on the left-hand side here via the Transit Gateway. We also realized that through customer feedback, a lot of customers wanted to communicate with all of our other public services like Lambda, SQS, SNS, Amazon Kinesis, etc., in a private means, so not having to go out the internet gateway. So we also built this service called Private Link, and that allows you to connect to private link enabled services, but also you could run your own SaaS or software as a service VPC, which has a private link endpoint associated with it, and then run your own service and drop that privately inside a VPC. We also have VPC flow logs, allowing you to gather metadata on traffic going in and out of your VPC. You can ship those off to Amazon CloudWatch or Amazon S3. And then we have Global Accelerator sitting out there in the public realm, allowing you to do advanced routing back to your VPC from the public realm. Now, what we see here is it's just a combination of a whole bunch of services that wrap around an Amazon VPC and allow customers to build scenarios in AWS where they could connect to their on-premises, they could connect to public services, they could allow public services or things to connect to them. And generally speaking, when you think about an Amazon VPC architecture, you're probably going to end up using one or many of these components that you see here. All right, so let's talk about Amazon VPC networking for AWS Outposts. So again, we've got the region on the left-hand side here. We've got our VPC, our availability zones, our public subnets, private subnets, instances that run inside those subnets. So our EC2 instances there. And what we're actually doing with Outposts is extending that VPC through to the AWS Outpost that's running on premises. So what we can do here is once we've got an outpost that's online, we can create an outpost subnet, create instances that run inside the subnet. And then because we're using Amazon VPC, we get access to route tables, security groups, network ACLs, all of the same constructs that you had access to inside the VPC, inside the region, you can now use in your outpost. And so what that means is we've now got instances running in subnets inside an outpost. We can also communicate from the region to those instances. So if we think about some traffic paths here, instance Y inside one of our outpost subnets can absolutely talk to instance Z inside one of the other subnets. But we can also have this cross outpost to AWS region or intra VPC communication from the outpost back to the region. So in this case, we could communicate from instance Y back to instance B or instance D if we wanted to. Now, the way we do that is through the route table of the subnets inside the outpost. So again, we have this local route, or the 10.100/16 in this case, via local, and that's going to allow connectivity across the VPC or inside the VPC. Now, what we can then do is have something like an internet gateway in the region, and an internet gateway is a region level construct. It's a hugely scalable entity that we manage, and you can use a slice of attached to your VPC. And an internet gateway obviously gives you access to the internet or other public services if you're not using private link. But in this case, our route table for our first Outpost subnet actually has a default route via an internet gateway, and we could communicate out to the rest of the world. Obviously, we need an elastic IP. It's associated with the instance inside the Outpost. But now we're communicating from on-premises, intra VPC, out an IGW, and to other AWS services. Likewise, we can connect to other services in the region as well. So we could have a VPC endpoint like we had earlier, maybe transit gateway, VPC peering, a VGW connecting to other on-premises if you wanted to. And you'll notice we build out our route table for the Outpost as we're adding components inside the VPC inside the region. Now, one of the main benefits of having an AWS Outpost on premises is low latency access to your on-premises workloads. So in this case, we've actually built a new type of gateway. The new type of gateway is actually called a local gateway, and it operates very similar to an IGW. So in this case, we configure another route for our on-prem routes or workloads that operate in our on-premises where the Outpost is, and we send that traffic towards the LGW or the local gateway. Now, just like an internet gateway in the region, the local gateway actually needs elastic IPs associated with it. So in this case, what we're actually going to do as part of the provisioning of an Outpost is ask you for a customer-owned IP range. In this case, we've got a 10.10.0.0/26, for example, and we've assigned a 10.10.0.21 address to our inside or VPC IP, the 10.14.11, which is actually instance Y. So what's going to happen here is traffic will go out and follow the route to our on-premises routes for the route table for our Outpost subnet. As it goes over the local gateway, the 10.14.11 will get source natted to the 10.10.0.21. And that's just so we have a clear perimeter between the VPC routing, and in this case, the VPC CIDR 10.1.0.0/16, and then how you represent the Outpost on premises. And we'll talk more about that when we get into the LAN configuration. Now, another quick point to make here is an Outpost isn't just designed to communicate with you on premises. Once traffic leaves the Outpost from your VPC, you could actually route that traffic anywhere else you wanted to. You could route it back to AWS via a private virtual interface and a direct connect if you wanted to. And in some cases, that absolutely makes sense. All right, so let's dive into the local area network connectivity. So when we talk about AWS Outpost LAN access, we're talking about connecting the AWS Outpost directly to your on-prem network. And so in the Outpost, we might have a VPC. We've got a CEDAR address range of 10.1.0.0/16. It might be extended from the region or not. You actually don't need to extend your VPC from the region. You could just operate things inside the VPC, inside your Outpost if you wanted to. And then we've built a subnet. In this case, we've got an EC2 instance there. And then we have these devices that sit at the top of the rack. We think of them like a top of rack switch, but we actually call them an Outpost networking device. And in fact, if you've ever seen a photo of an Outpost, these are the two devices that sit right in the middle of the Outpost rack. The fiber patch panel is actually what sits at the top of the rack that customers will connect into. But in this case, we're connecting to customer networking devices, and there's a demarcation here. So anything south of the port of the patch panel that you'll plug into with an Outpost is AWS's responsibility, and anything north of that patch panel connected to your customer devices is your responsibility, including the fiber patches as well. So what we'll do here, and in this case, we're going to use a couple of physical fibers, but we need to connect physical connections from your customer networking devices to our Outpost networking devices. So we support single mode or multi-mode fiber with LC connectors. We also support connection types of 1, 10, 40, or 100 gig. And we do ask for a minimum of 2 connections. So in this case, we're actually showing 4 connections, but we do ask for a minimum of 2 connections or 1 connection per Outpost device. So what we'll then do after we've got the physical connections plugged in, we'll put these into a LACP group or a link aggregation. So these connections will actually be part of a a logical connection or port channel between our networking devices and your customer devices. And what we'll then do is we have two different types of connectivity that the Outpost needs to have. One is the service link connectivity, and the other is the LGW connectivity. So we'll actually ask for two VLANs for the service link connectivity. In this case, it's one per device. And that VLAN will be what the Outpost uses to connect back to the region. And we'll talk more about that in depth when we talk about the WAN connectivity. Then we'll also configure the LGW VLANs, so another set of VLANs on each device, which will also be trunked over the logical or LACP connections. And we'll also ask for a /30 or /31 set of subnets between each devices. So for the service link, we actually have two subnets, or 2/31s in this particular scenario. And that's because these VLANs are actually point-to-point VLANs. So they're not VLANs that will get layer 2 extended all the way through to further parts of your data center. They're actually designed to be just point-to-point VLANs between the Outpost networking device and your directly connected customer networking device. We'll also do the same thing for the LGW side of things. So we'll use the LGW subnets to configure point-to-point VLANs as well. So similar to the service link VLANs, the LGW VLANs are also point-to-point VLANs, and we ask for another /30 or /31 subnets for those two. So next, for the Outpost itself, we'll ask customers to assign a /26 for what we call the service link subnet. And the service link subnet is what we use to address the Outpost from an infrastructure perspective and how it reaches out back to the AWS region. So in this case, we're using a 10.500/26. Now, over the top of our service link VLANs, we'll also run BGP. And BGP, or Border Gateway Protocol, will advertise the service link subnet, in this case the 10.500/26, over two BGP sessions within the service link VLANs towards your network or the customer network. And what the service link is actually used for is control plane and data plane back to the region. And we'll talk more about that when we move along to the WAN connectivity piece. Additional to the service link subnet, we'll also ask for an LGW subnet, and we're calling this the customer owned IP range. And so in this case, where we can configure a /26 as a minimum, or we'd probably prefer something larger, but the LGW subnet is what is going to be used to address EC2 instances inside the VPC. And so they're publicly reachable from, or reachable from, anything within your data center. Now, again, on the LGW side, we'll also use BGP. So we'll be advertising the LGW subnet here, the /26. And that's actually going to be routed through the LGW. So if we think about this from a traffic path perspective, we'll configure routing within the subnet of the VPC inside the Outpost. And you'll notice here we've got our on-prem routes or on-premises routes via the LGW. That'll then send traffic to the LGW, and the LGW or local gateway will route traffic through up to the LGW VLANs and onto your on-premise network. Now, the LGW is actually performing a NATing function here. So if we think about EC2 instances that sit inside the subnet of your VPC inside your Outpost, they will be addressed inside the VPC seeder address range. But the local gateway will be NATing that address range, or single IPs or Elastic Network Interface addresses will be NATed at the local gateway, just like an internet gateway. Okay, so that's pretty much it from a LAN perspective. And as you can see here, the Outpost needs connectivity back to the region via the service link, but we also have the LGW subnet, which allows connectivity through to your on-premises. So we announced general availability of AWS Outposts on December 3rd, 2019, and that was actually during reInvent last year. At that same time, Jeff Barr actually released a blog post, and we can see here there's actually a photo of the Outposts, and if you look really closely, you can see the networking devices in the middle of the rack there. But more importantly, on this blog post, We actually have two reference architectures, one from Cisco and one from Juniper. So we worked pretty closely with Juniper and Cisco during the launch of AWS Outposts. And the reference architectures that you can visit here via the blog, and I'll throw a link towards the end of the presentation for this. These reference architectures help you understand how to configure the customer device side of the Outpost. So there's a whole bunch of reference templated configurations and that sort of thing, both for Cisco devices and Juniper devices. Definitely worth checking out if you're interested in what the customer device side of an Outpost configuration looks like. All right, so lastly, let's dive into the wide area network connectivity piece for AWS Outposts. So when we have an outpost, we've obviously got the region, and the outpost is designed to be always connected back to the region. So within the region here, in this case, we've got a VPC. We've got a CEDR address range of 10.100/16, some EC2 instances, and then we have our customer on premises on the right-hand side here. And so with our customer on premises, we've deployed an outpost. An outpost is also a EC2 based service as well. So I like to think of outposts as having EC2 available and other services like EKS, ECS, RDS, etc. But then we have our outpost devices with our local connectivity, or maybe back to AWS if we want. So our LGW, and that's the blue connectivity that you can see here. But then we have the service link. And in this case, again, we've got a 10.5.0.0/26 for our service link subnet. And we need that to be able to connect back to AWS. So in this case, at the customer premises, we've probably got a customer edge router, or what's normally called a CE or a CPE device, a customer premise edge device. And we probably have some form of WAN connection. And for the primary connection here, we're actually going to use AWS Direct Connect. So with Direct Connect, we've got a whole bunch of points of presence across the globe where you can connect back into AWS. And we don't give out the address of our data centers, but we absolutely give out the address or locations of our Direct Connect POPs, because what you can do here is you can deploy a device at one of these locations in a customer cage, and then use what's called a cross connect to connect from your device to an Amazon or AWS device. Now, with Direct Connect, we're essentially leasing you the port on a Direct Connect POP router, and then you have the ability to segment that or carve that physical port up into virtual interfaces, or what you see on your side is essentially VLANs or virtual LANs. So in this case, for connectivity of the outpost back to the region, we need public connectivity. So we're going to build a public virtual interface. And so with any public network, and with the service link range being a 10.5, which is actually a private RFC 1918 range, we need to NAT to something public. So in this case, we might be doing some network address translation here at the customer edge router, or in a lot of cases with a public virtual interface, we'll NAT at the edge at the customer POP, or customer point of presence. So in this case, we're actually NATing the 10.5.0.0/26 to something public. So once we've got our public virtual interface set up and we've got public access back to the Amazon region, we'll use that to connect back to what we're calling the AWS Outpost Service. Now, when you create an outpost or you purchase an outpost, you'll choose what region you'd like that outpost to be home to, but also what availability zone you'd like the outpost to be home to. Because what we need to build from a control plane perspective is connectivity from the outpost back to this AWS Outpost service. And this Outpost service is actually fronted by Amazon public IPs. So they're IPs that are publicly reachable from the internet or a public virtual interface. So in that case, you could actually use an internet circuit as a backup for your Direct Connect for Outpost access, or you could use it as the primary. And the main reason why we chose to use Amazon public IPs to front this Outpost service was that we wanted to reduce the barrier for entry for folks when they wanted to use an Outpost. So AWS Direct Connect isn't an absolute requirement. If you wanted to use Outpost, you could just use a standard internet connection. We do, however, ask that for WAN connectivity, you have at least a 1 gigabit per second connection. So either a 1 gigabit per second internet connection or a 1 gigabit per second direct connect connection. And the reason why we ask for so much bandwidth is not that the outpost will be sending that much bandwidth all the time. But when you spin up EC2 instances inside an outpost, it will do things like provision the EC2 instance, but use an AMI or an Amazon machine image that might be sitting in the region. And so if you have a 1 gig connection, the download of that AMI is actually something that goes a lot quicker than if you only had, say, a 10 meg connection. And if you had a lower bandwidth connection, you'd actually get a poor experience when you're using the outpost. So we do ask for at least a 1 gig connection. So once we have that WAN connection back to the region, and in this case, we're using the direct connect as the primary, we'll build what's called the service link back to the Outpost service. Now, the service link itself is actually a set of custom VPNs that we provision from the Outpost. So what's not shown in this diagram is that a lot of customers will actually have a firewall between the public realm and their local data center realm. So in that case, when we provision or bootstrap the Outpost and turn it on for the first time, it will actually try and call home, and it will try and reach to these Amazon public IPs that we've designated to the Outpost service. And so in that form, you actually need to take your stateful firewall, if you have one that's sitting in line, perhaps between the Direct Connect public virtual interface and your on-premises data center, and configure an outbound stateful firewall rule for TCP and UDP destination port 443 with the source port of the ephemeral port ranges. And in fact, those details are located in our documentation, which I'll throw a link in the end of the presentation here. So once we have the service link and we've brought that service link or VPN connections up back to the Outpost service, we now have control plane connectivity to the Outpost. So this is how AWS manages the Outpost. So remember earlier we said that an AWS Outpost is a fully managed service, and we, AWS, will manage the Outpost from the region via this service link connection. So whenever you're doing an API call through maybe the AWS console, and you're provisioning an EC2 instance within an Outpost, that call will actually go over this service link connection. Now, likewise, for data plane traffic, we actually had a VPC architecture earlier where the VPC spanned both the region and the Outpost. So the connectivity from that VPC to the Outpost is also via the AWS Outpost service and the service link. So in this case, if we've got an EC2 instance on the right-hand side and it's communicating with other EC2 instances inside the Outpost, that's fine. That traffic remains inside the Outpost. But if one of those EC2 instances wants to communicate with the region and an instance that sits inside that same VPC, that traffic will actually go via the service link. So as we can see here, we've actually got a path that goes from the EC2 instance on the right-hand side from the Outpost over the service link, which goes over the direct connect. And you can think of the service link like an overlay network that sits on top of the direct connect. And your direct connect is really the underlay physical network. And so the EC2 instance inside the Outpost will traverse the service link over the direct connect, over the AWS Outpost service, and down through into the VPC and connect to instances inside that VPC. So now what you can see here is we've got two paths exiting from the Outpost. You've got the LGW or blue path, which is going to be native traffic that goes over the local gateway and through to your on-premises, or that traffic could go over a direct connect natively back to a region if you wanted to. Maybe you've got a direct connect that connects you through to an Amazon VPC via a private virtual interface or similar. And then we've also got the yellow path here, the service link path, and that's going to be the overlay connection on top of the direct connect. And that connection is going to allow both control plane going back to the Outpost and also data plane going from the Outpost through to the VPC inside the region. Now, there are some services that operate within the region solely, and I just want to call those out really quickly. So one of those is Transit Gateway. And in fact, we don't have the ability to run Transit Gateway natively inside an Outpost because Transit Gateway operates on what we call Hyperplane. And Hyperplane is a service that AWS built for things like Network Load Balancer and Transit Gateway. Now, Hyperplane is a hugely scalable service that needs the region to operate. So in that case, if you did communicate from an Outpost to a transit gateway, you'd actually transit over the service link and through out to the transit gateway that sits inside the region. Now, some other services like VPC peering, for example, and you can actually have multiple VPCs inside a single outpost. If you did peer VPCs inside a single outpost, traffic wouldn't need to go via the region. It would actually transit from one VPC to another via that peering connection inside the outpost. So there's definitely a few things to think about when you think about traffic flows. And what I always recommend is to sit down with your application owners and figure out where traffic is sourcing from and what the destination is, whether things are operating inside an outpost, operating inside the region, or even operating on premises. It's always a good idea to define those traffic flows. And then you've got a bit of an idea on how to provision your routing and your connectivity and who needs to communicate over an LGW or who might need to communicate over a service link. Okay, that's all I've got for you folks today. Just a couple of links here to follow up on some additional reading material. So the first one I'd recommend is the AWS Outposts overview, and that's our main landing page for anything like this webinar and other content, and that can be reached at aws.amazon.com/outposts. But then we've also got within and as part of our documentation how Outpost works. And as part of that piece of documentation, we actually run through the different layers of an outpost, including LAN connectivity, WAN connectivity, etc. So a lot of the things we've spoken about here today are actually found in that how AWS Outposts works content in our documentation. And lastly, one of my favorite blog posts, I'm a little bit biased though, the Jeff Barr blog posts with the launch of Outposts last December. And you can reach that from the link here below. So the AWS Outpost now available blog post. And within that, you can link down through to the Cisco and Juniper reference architectures that I mentioned earlier. And thanks everyone for joining today. I'm Matt Lewis, Principal Developer Advocate for AWS, and I hope you folks learned a few things about AWS networking and see you next time.